So here we are in the second video of electrochemistry, and let's go back to our lemon battery. And inside of our lemon battery we've got a strip of zinc right here, and then we have a strip of copper right here. This is a strip of iron that I'm just going to take out of the situation right now. And we can see that our voltmeter reads about 1 volt or so, our multimeter. And so we have electrons passing from one place through here, through the voltmeter, over here, and into the copper right here. This voltmeter, or this measuring device, is called our load, and that is the thing that's detecting or using the electrons as they pass through these wires. We could hook a light bulb or something else up if it would actually function on 1 volt with this amount of electrons flowing through. It would actually work. Now here's an atomic level description, just using our descriptions of chemical equations that kind of shows this. Our zinc right here is this strip right here, this metallic strip. And then this says it's in nitrate, but it isn't in nitrate. It happens to be inside of a lemon. And so you can think of this as like the inside of the lemon right here. And the reaction going on inside the lemon is that the zinc right here is being oxidized. And so zinc is actually dissolving inside of this lemon. And then the electrons are given up right here, and they're actually being pulled through this wire right here, all the way through the multimeter, and then they're being sent over here to the copper. And then looking at the other part of the reaction that's going on, copper over here is actually gaining the electrons. And it says that there's nitrate right here, but there's really not. We're inside of a lemon instead of that. And this copper right here is undergoing a reaction where copper is gaining electrons and becoming copper solid. And that transfer of electrons from one space to the other is what causes a current. We call it a current of electrons, and that's what causes electricity to flow. We'll put some fancy names to these electrodes right here. We'll call the zinc an anode, and we'll call the copper the cathode, and then we'll look at how much certain metals want electrons versus others. And we'll look deeper at these electrochemical cells as we go along. But before we can do that, we've got to put a little bit more mathematics to our describing or our description of electrochemistry. And so in step number 2 right here for electrochemistry, we're going to look at balancing redox reactions. We'll come back to our galvanic or voltaic cells here, and we'll look at our batteries, and then more here in number 4. But today, we're going to look at balancing redox reactions. It's a 6-step process, and it's going to fill up a page right here. It's got a bunch of sub-steps to it. It's long, difficult, and challenging, so make sure you've got a piece of paper and a pencil handy so you can write down the steps, and I'll do 2 example problems, each which take a number of minutes to work. So when you balance redox reactions or oxidation reduction reactions, the first thing you want to do is take whatever reaction you're looking at and assign the oxidation numbers so you can split it into its half reactions. Half of a reaction is going to be oxidation, the other half will be reduction, and being able to assign the oxidation numbers and then decide which one is which is critical. So then we're going to take and balance each half reaction separately, and there's a specific order in the steps that we do to balance each half reaction as we go. Step number 1, balance any other elements other than oxygen and hydrogen. Step number 2, balance oxygen with water. Most redox reactions occur in aqueous solution, and so water molecules are plentiful, and so we can use those water molecules inside the aqueous solution to balance the oxygens on the reactants or the product side for each half reaction. Step number 3, add H pluses to either side of each half reaction to balance the hydrogens. Now we're assuming, and it's a fair assumption, that these redox reactions are happening in an acidic solution. Our lemon cell is a perfect example because, of course, the lemon cell has citric acid inside of it. And so there are H pluses that are plentiful to help us balance that part of the redox reaction. And then lastly, use E minus to balance the charge, and whatever number of E minuses we may need to make the one side of the reaction have the same charge as the other side of the reaction is our job. Step number 3, multiply each half reactions so the electrons are equal. Multiply each half reaction so the electrons are equal. Sometimes you don't have to multiply them at all. Sometimes you have to multiply only one half reaction. Sometimes you have to multiply both. Once you're done making sure the electrons are equal, add the half reactions together and simplify. Cross off anything on both sides of the reactions that's the same. Step number 5 takes care of our issue if it's not an acidic solution, like if it's in a basic solution. Then we add OH minuses to eliminate the H pluses. I'll do an example of a basic solution one and you can see how that works. And then step number 6 is to check. Check to make sure that we're balanced for mass and check to make sure that we're balanced for charge. So example problem number 1, let's take a look at a reaction that we looked at last video cast, and then let's see if we can balance it. So here's our one-page example on acidic solution redox reaction. If you wrote these out nice and large like this on one page, maybe go to the page next to it and put this reaction at the top of the page. Pause the video now if you need a little bit more time to make sure that you've got the charges correct and the subscripts. Balancing redox reactions is a very detail-specific process, and so become very, very picky about writing your subscripts, also writing your charges in the upper right-hand corner, being very, very particular about them. Also, you'll notice that everything in this redox reaction is aqueous, and since it's aqueous, we have lots of water molecules around to help us. So step number 1, split the half reactions. And to be able to do this, to split it into two half of the reactions, we need to assign oxidation numbers. And we did this last video cast, and if you want to go back and look at how we did this, making sure that each of these sums up to 0, sums to +2, sums to -2, -1. That's probably a really good idea. Now we can see that manganese goes from +7 to +2, and so our half reaction for manganese will be MnO4- goes to Mn+2, and our half reaction for the oxalate ion will be C2O4- goes to CO2. So our manganese-containing species and our carbon-containing species. All right, step number 2, balance everything other than hydrogen and oxygen. Manganese and manganese, they're okay. Carbon and carbon, oh, it looks like I'll need a 2 right here to balance the carbons. Step number 2, balance the oxygens by adding HOH, or water. There's 4 oxygens here, so that means on this side of the reaction, I'm going to need 4 waters to balance out the number of oxygens here and the number of oxygens here. There's 4 oxygens here, and there are 2 times 2, or 4 oxygens there, so I do not need to add any waters on this side, or either side of that half reaction. Balance the hydrogens with H pluses. There are 8 H pluses right here, so I will need 8 H pluses on this side of the reaction. And then there aren't any hydrogens in this reaction, so there's no hydrogens to add for that one. And then use electrons to balance the charge. So now we need to go through and look at this entire half of this side of the half reaction and add up the charge. There's 8 positives here, 1 negative here, so that means the total charge on this side of the half reaction is +7. And the total charge on this side of the reaction, this is 0, this is +2, so +7 to +2. That means to make these two sides equal, I will need to add 5 negative species to this side. So I'll add 5 electrons right here. If I do that, now my charge is +2 on this side and +2 on this side. Down here, I've got an overall -2 charge, and over here I have a charge of 0. And so I need to make those equal to each other, so I'll add 2 electrons to this side to make sure that this is -2 and now this is -2, and they match from one side to the other. Notice how 1/2 reaction had electrons that were gained and 1/2 reaction had electrons that were lost. And so, as we've said before, this is my reduction half reaction because it's gaining electrons and it went down in charge. And then this is my oxidation half reaction, and you can see that it went up in charge from +3 to +4. So now on to step 3, multiply the reactions so the electrons are equal. And I can see I have 5 electrons here and 2 electrons here. So when I rewrite this half reaction right here, I'm going to multiply this one by 2. So I get 10 total electrons. And I'm going to multiply this reaction by 5. So I get a total of 10 electrons over here. Then the electrons would be equal on each side. I'm going to rewrite both of these half reactions right down below here. First of all, when I multiply this by 2, I get 16 H pluses and 2 MnO4 minuses, and then 10 electrons. And then on this side, I'll get 2 Mn positive 2s and 8 HOHs. In this reaction, I'll multiply everything by 5, so I'll end up with 5 C2O4 minus 2s, and then 5 times 2 is 10 CO2s and 10 electrons. Notice my electrons match my electrons. That's why I did the multiplying. So then when I do step number 4, I'll be able to add both of these half reactions together and take everything on this side of the half reaction and put it in one side, and everything on this side of the half reaction and put it on the other side. And then I'll be able to cancel any like species to make it a completed balanced reaction. So this side of the half reaction, I'll start way over here on the left side of my page. 16H plus 2 MnO4 minus plus 10 E minuses plus 5 C2O4 2 minuses. You got to be really picky and careful to make sure that you get all of the little numbers each time that you rewrite it. Many opportunities for error, and I hope I don't make one here. 2Mn plus 2 plus 8 HOHs plus 10 CO2s plus 10 electrons, I think brings everything from this box down here onto this side of the reaction. All right, we're not in basic solution, so we don't have to do step 5, but we do have to simplify right here in step 4, and simplifying means getting rid of these electrons right here, and then anything else that's the same I can eliminate as well. And it looks like everything else is individual, and so this underlined portion would be my balanced redox reaction. And let's do step number 6 now. Let's check and make sure that it's balanced not only for mass but also for charge. So when I say balanced by mass, let's make sure that there's 16 hydrogens on this side. 8 times 2 are 16. So for H's, we've got 16 on both sides. Number of manganeses, I have 2 manganeses on this side and 2 manganeses on this side. Carbons, I've got 10 carbons on this side, 2 times 5. I also have 10 carbons on this side. And then lastly, I have 8 plus 20, 4 times 5, right? Or 28 oxygen atoms. And then over here I have 10 times 2, or 20, plus 8 more is 28 oxygen atoms over here. So it's balanced for mass. And then let's just check to make sure that it's balanced for charge. So I need the overall charge of the reaction on this side, which is 16 positives, 2 negatives, so that gives me minus 14, and then 10 more minuses right here. So that gives me a total of positive 4, I believe, on this side of the reaction, if I did that math right, and I'm not promising that I did. And then over here I have 0, and then 2 times positive 2, or a total of positive 4 on this side. They match, and if everything matches, then you can jump up and down and say, congratulations, you just balanced your first redox reaction. So I'm going to do a second example redox reaction now, and this one is in basic solution. But before I do this, I'm going to pause the video cast, and I'll make this a separate one for the balanced in basic solution.